Good morning. Thank you for attending our webinar. My name is Šimon Rajčan, and together with my colleague Petr Hájek, we will talk about enterprise data lineage for analytical superheroes. Firstly, we will have a small introduction. There we will do some follow-up on our first webinar, which was more oriented on business side of integration of various metadata sources to a metadata warehouse. Then we will talk about basics of what is data lineage and what is enterprise data lineage. I will explain about graph structures and traversal algorithms. And I will also talk about static or dynamic data lineage. After that, my colleague will go, let's say, deeper into how to achieve this data lineage. So he will talk about vertical or horizontal aggregation. He will tell you about the closest neighbors method. Then he will explain edges valuation relevancy, and he will tell you what to do if there are missing links or bridges over your data lineage. And at the very end, because in some cases we know that simple data lineage may not be enough, he would explain you what is conditional data lineage and how to achieve it. As I said, the first webinar was more oriented on business usage of metadata warehouse. We also introduced our solution Impact, which has a pre-built core model inspired by data vault techniques. We also said that data lineage metadata is a must when we talk about such integrated solution. And we explained other metadata sources and their business value to the whole integrated warehouse. We have also shown reasons why we believe that simple integration of one metadata source to another without a proper warehouse may not be enough, especially in a long-term maintenance. And today's webinar will be oriented solely on data lineage and enterprise data lineage, where I will talk about the basic definitions, and my colleague Peter will talk about or will go deeper to explain several technical obstacles when trying to achieving this data lineage. So let's go to the basic definitions. What is data lineage? Data lineage is about following dependencies in data flows between objects, like for example, tables. And those objects are connected by transformations, which could be ETL process, SQL procedure view, etc. Typical data object which persists data is a database table or dataset, but it can also be any file or report or any other object. We can also follow dependencies between systems, not just within one database or several databases. And those systems can or very usually are built in different technologies than SQL. We can use data lineage in various scenarios, like for example, defining a subset of objects for better focus testing when there is a new release, or identifying a subset of systems to migrate them into cloud per partes. Or we can use it for sensitive data tracking if, of course, we have conditional data lineage, which we will speak about later. When we talk about enterprise data lineage, we mean that we don't follow the data flows in one system, usually data warehouse, but we have to scan and follow the data flow in multiple information system, let's say most of the system within an enterprise. Those systems usually are built in different technologies, platforms. It could be relational databases, big data, reporting, or operational systems, both in cloud or proprietary. This slide is showing a real example of such enterprise data lineage. So there are many systems which are like objects, and there are many flows between them. If we want to work, if we really want to work with data lineage, we need to understand what is graph structure and the traverse algorithm. Because data lineage is described by metadata in specific format, and this format is simply a graph structure. Such graph has nodes and edges, where node represents any type of object and edge represents any type of data flow from one object to another. That means that we need to have a set of objects and edges and their attributes to describe this data lineage. And if we have it, we have to use, or we can use, a traversal algorithm, which is a complex algorithm with recurrencies, loops, and many nested steps or levels to visualize the data lineage from that graph structure, or from that graph structured metadata which describes it. If we talk about data lineage, we can we can distinguish between two basic approaches. Code-based lineage scans a code, usually SQL or other languages that describe data flows. And the event-based lineage is a path in the event processing network that enables the tracing of the consequences of an event, or finding the reasons for a certain action. That means scanning kind of business processing system. But usually, or in most cases, code-based lineage is used. And the last definition from my side, code-based lineage is or can be split into static or dynamic. When we talk about static lineage, it is a simpler one. It detects dependencies in deployed software artifacts like select from, insert into, and we can do a semantic analysis of such code. And from that, we can get desired nodes, set of nodes and edges. The problem may come if we talk about dynamic lineage, when the code is generated based on each execution. So there is basically nothing to read. In such scenarios, we have to firstly run the code to be generated. So all the SQLs and other codes is generated. And then we have to somehow store it, for example, to logs. And after that, we can scan the logs the very same way like when we do static code lineage. So that was the basic definitions. Now I would like to ask the attendees whether their company is or is planning to use data lineage. So you can choose any option now. There is only one answer that yes, we have a data lineage tool and we are using it regularly. In most of the time, there is a tool, but the usage is limited. That's also our experience. And there are only two answers that no, we don't need it and we don't even consider it. So thank you for your answers. Now I'm handing it over to my colleague Peter. I'm handing it over to my colleague Peter, who will talk about enterprise data lineage techniques and obstacles when achieving it.
Well, if you want to succeed in enterprise data lineage, you will have to face the following challenges. Let's start with the first of them, the easiest one. I call it vertical aggregation. In this example, we have metadata describing data lineage tracked in two systems. First system is built on Oracle relational database, and the second is Tableau, which is reporting tool. In case of Oracle, like any other relational database, the situation will be quite simple. Typically, data objects are organized in simple hierarchies. In this case, we can see table columns, which are organized in tables. Tables are organized in schemas, schemas organized in databases, and this belongs to the whole system. But in case of other technologies, like Tableau, for example, you will see much richer hierarchy and maybe even some embedded objects, like, for example, one report is embedded into another report and so on. And if you want to work with the metadata in the same way, we need to do something. I call it leveling or nivelization or vertical aggregation. Simply, we need to decide which types of objects in specific technologies, or maybe even specific systems built on the same technology, will be assigned to specific predefined levels, or even we can call them layers. If you look at enterprise data lineage, like drawing a digital map, you can imagine that your map will have several layers, each layer with different level of detail. I suggest that we have no more than 4 layers of our map, and each layer is defined with different specific types of nodes. Starting from the top to bottom, we can see that the highest level is built using root nodes. So we will define root nodes at the level of the whole systems or individual technologies, like Oracle system, reporting system, and so on. One level down, we will see a layer which is built using what I call cluster nodes. For databases, we may assign all database schemas to individual cluster nodes, or we may decide that several schemas will be defined as one single cluster node. In other technologies, like reports, we can, for example, define the whole Tableau site as one individual cluster node. Going another level down, we define what I call master nodes. I think this will be the most frequently used layer. And we will assign all database tables to individual master nodes. And for example, we will decide that all reports will be marked as individual master nodes. And on the bottom, we will see the most detailed level of what I call leaf nodes. And typically, if you use some reverse engineering tool to harvest your data lineage metadata, you will get your data flows and dependencies defined on column level, which means database tables, columns, and items of your reports and other types of objects will have drawn edges in your most detailed level of your graph on leaf nodes. But there will be too many leaf nodes and too many edges drawn among them that you will need to do something like aggregation. And we will look at it on the following slides. But for now, let's complete this first challenge with just having your metadata aggregated to just 4 levels: root nodes, cluster nodes, master nodes, and leaf nodes. Still, your graph dependence or dependency of your data graph of your data flows will be too rich and too complicated to be visualized and read by humans. So we will need to do something more. If you start your traversal algorithm, you typically select a certain point in your graph schema or your graph chart. It may be a simple report or a specific table in one of your systems. And then you decide that you will traverse backward to the data sources or forward to data targets. But once you start traversing, you may start asking yourself, how many steps do I need to go back? Is it just one step, or do I need to go back to the very first source of my data or the very last target? Or can I stop somewhere? Also, you will start asking yourself if you are supposed to traverse all the branches, or if you can stop at certain point in a specific branch, or if you are really supposed to traverse to all branches around your specific data object. Another task or challenge that you will face is that you will find that there are some cyclic dependencies. You start traversing at a certain point, and after a few steps, you realize that one of your branches has led you back to the original point. In this case, there are several techniques what you can do. The simplest one is that you simply stop, you record the information about the cyclic dependency, and you continue traversing with other branches. Anyway, still our graph is too complicated to be read by humans, and we need to continue with the aggregation of our metadata. In this case, you can see that there are leaf nodes, actually 15 columns on the level of leaf nodes, and there are 12 gray edges which represent column level mapping or dependencies among these columns. If we aggregate this information about column level mapping to the level of master nodes, tables, and procedures, we will end up with just 5 master nodes and just 4 edges, explaining that there are some dependencies between table A, which is read by procedure A, and data is written to a table B. So we simplified. Now it does not give us that much of simplification, but if you imagine that there are thousands or maybe hundreds of thousands or even millions of leaf nodes, column level dependencies, this simplification can be very beneficial. But you may go even further. You may decide that specific types of your data objects will be ignored or will be skipped. In this specific case, we decided that for the purpose of our analysis, we are not that much interested in the information what happens with data flowing from table A to table B. We are just happy with the fact that there is a dependency, that table A is a source for table B. And we will for now ignore how many columns are linked to this dependency, or how many procedures realize some data flows. Simply, we will end up with 3 master nodes, tables, table A, which is source for table B, and B being source for table C. So we have only 3 nodes and 2 edges now. If we visualize the same information in a graph format, you will see that we have these 3 tables and 2 edges again, which is much simple information that all these more detailed edges and nodes that you can see in a gray color in our picture. But again, we may continue even more in our attempts to aggregate or simplify the whole schema. And we may to decide you may decide to encapsulate or aggregate some specific subsets of our nodes. In this case, table B, procedure B, and table C belong to the same, let's say, module of a specific system, or it can represent a specific facet of a data model or something like that. The important thing is that for now, it is important to know that table A is a source of some data for the whole encapsulated set of nodes, table B, procedure B, and table C. Looking at the graph picture, we see that we have only one table, which is a source, and one edge leading to this encapsulated set of nodes. So again, significant simplification and ending up with just information that there is one real dependency, which should be taken seriously in our analysis. By doing the previous two operations, vertical aggregation and horizontal aggregation, we may very easily prepare a set of data, which I call the nearest neighbors method. It means that for a selected types of nodes, let's say for all the master nodes in our schema, it means for all the database tables and all the reports, we will run our traversal algorithm with the condition that we stop traversing in all the branches once we visit the nearest neighbor of the same type. So starting from a specific table, we will traverse all the branches, all the directions, but only up to the point when we reach the nearest table or nearest report. Doesn't matter how many tables, how many columns or how many transformations are covered or hidden behind these aggregated edges. The important information is that we stop at the nearest node of the same type. And this way, we can prepare new set of metadata, which we can further use in other instances of our traversal algorithm, but now we are traversing in the upper aggregated layer of our map. And this can be very useful information. We can use it not only for visualization of data lineage, but for example, we can use this information if we want to understand what happened with our systems. For example, once new releases of new versions of these systems have been deployed. It means we can scan all the versions before specific release and after, and then we can compare and we can find out which objects, which, let's say, master nodes of our graph charts have changed their neighbors. And we may find that, for example, only 15% of our tables or reports have changed their nearest neighbors, and we should maybe focus on them when planning the testing phase or something like that. Okay. If we manage to do these aggregations and maybe we prepared a list of the nearest neighbors, we may realize that some pieces of our data landscape maps have blank areas, white spots. Not always we will be able to collect good quality of metadata for all the systems that we want to understand or map or analyze. Similarly, like on these examples of terrestrial maps, there are some places where we need to use some other sources of metadata. In this example, I have end-to-end data lineage, which uses harvested metadata. It means metadata that I got using a reverse engineering tool. And some pieces of the data lineage are covered by alternate source of metadata. In this case, I call it modeled metadata, or metadata which I got, for example, from a power designer or enterprise architect or any other modeling tool, which gives me typically some information about data flows, but usually not that detailed as harvested metadata. But if I don't have harvested metadata for any reason, for example, it's built on technology which I cannot read, I cannot parse it, or whatever other reason, maybe I didn't get enough access rights to read that system. So I need to help myself using other source of metadata. In this case, modeled, for example, Power Designer metadata. But I need to do at least one of the previous techniques. I need to do vertical aggregation to make sure that I align all the metadata sources at the same level of detail. In this case, this is level of master nodes. And second, I need to be able to identify that specific nodes, which can be found at the borders of these pieces of my data landscape maps, are really the same. So in this case, I need to technically identify that table B in my harvested metadata is the identical object as table B according to my modeled metadata. And similarly, table C is the same as table C, the other place. I may use some techniques like naming conventions. I can parse connection strings in these systems and so on and so on. But at the end of the day, I really need to have the same IDs of the same objects and make sure that these are really identical. And that if I map these objects, I can draw the continuous lineage from very end to the very beginning of the data flow line. Well, now we are getting to the ultimate technique, which has already been presented by Shimon at the beginning, which we call conditional data lineage, but we need to make some enablers for this conditional data lineage. So far, you are focused more on the nodes of our graph structure. Now we are going to focus on edges, and we are going to evaluate the graph edges. Maybe we will evaluate the edges among leaf nodes, but very likely we will evaluate the derived aggregated edges on the upper layers of our data landscape map. There are three types of measures which we can assign to graph edges. The first of them is quantitative. We can collect information, for example, how many columns or tables are involved in the aggregated edges. Or we may use some other sources of metadata, and we may try to, like data profiling, for example, we may try to understand how many records flow through a specific edge of our graph, or how often do we run a specific transformation, which is represented again by the graph edges. Because it will be different information for us if we find out that through this specific edge of our graph, there are data flowing every minute in nearly real-time mode, or if we find out that this edge of our graph represents a transformation which is executed only maybe once a month, or is executed manually based on some ad hoc request and so on, which means that the relevancy of the graph edge will be different based on how often we execute it, or which amounts of data flow through the specific line. Then there are qualitative measures. We may assign information about what is the complexity of data transformation represented by a specific graph edge. Is it a technical transformation which simply takes data from one database technology to another, but does no changes in the content or structure of the data? Or on the other hand, is it a really complex business transformation which makes a lot of calculations, filtering, and aggregations, whatever we may imagine that happens with our data based on specific business rules and so on. It can be very useful information again, but it's more difficult to get this qualitative type of information and evaluate it and assign it to a graph edge. The most difficult task will be to understand or analyze the code snippets. Again, all the edges in our graph will be linked to some specific data transformations. These data transformations are typically implemented as a script. Most frequently, it will be SQL code script. And now imagine that you can go back into these snippets of your SQL code, and you may try to understand what where conditions, join conditions, having conditions, and so on are there, and which business rule they represent. By a lot of techniques, including artificial intelligence, you may be very successful in understanding what happens with your data just by analyzing, these code snippets. And again, based on this analysis, you may label your edges of your graph, for example, with the information that there is a specific filtering condition, like filtering out all the, let's say, customers who are retail customers. So you know that at the end of this specific edges, you will end up with data which are filtered. So you will not find data about specific product or specific clients at the end of each line of your graph. It may be very, very useful. And now imagine what we can do with this information which we assigned to graph edges. In our case, there are dependencies like table A, table B, table C, but we also technically see that there is a dependency between table B and table D. But for some reason, by analyzing the graph edges, we found out that for our analysis, for the purpose of our analysis, maybe this technical dependency B to D is not relevant. For example, this is just a technical transformation which has nothing to do with the business purpose of our analysis, or maybe that we found out that the data transformation filters out data which we are no longer interested in, or many other reasons which give us the information that specific edge of our graph is non-relevant or less relevant, and we can ignore it. So again, we can significantly simplify the picture and make it more human readable. I would say that these analytical techniques are really aimed to what I call giving human face to our data lineage metadata. It means making it more human readable. And these were 4 techniques: vertical aggregation, horizontal aggregation, bridging the gaps, and ultimately conditional data lineage, which we introduce in this webinar. And I would like to invite you to hackathon, which we call Hackflow. It will be held at Česká spořitelna in Prague in September 27th and 23rd this year, 2022. And we are going to invent or find out the most efficient and elegant algorithms which implement techniques for these 4 challenges: vertical, horizontal aggregation, bridging the gaps, and conditional data lineage. And we believe that we will really find nice techniques, nice algorithms, and we will end up with nice visualization of even very complex set of metadata, which we have already collected at Česká spořitelna. That's all for the webinar. And now I will ask if you have any questions. I see that there is a question. What efficiency do these presented techniques bring usually in your experience? Okay, this is a nice question. First, how we would measure such efficiency. The efficiency starts with the quality of metadata. You can have very good quality of metadata, and it means that the information is already inherently present in the metadata, and the task is only how to extract it, mine it from the metadata. Then if you are successful and if you really have nice algorithms for all these techniques, you should be theoretically 100% successful. Sometimes it isn't always a cost-benefit ratio, so you do not have enough time for completing the whole analysis, and you end up with identification of, let's say, only few relevant edges or few relevant types of objects, and it brings your analysis forward. I would say that the analysis as such is incremental process, or it needs to be executed in several steps. So you do high-level analysis, maybe you identify just the cluster nodes, and then you decide that several cluster nodes are not important for you, and you focus only on pieces of your graph, and you go down to more detailed levels like the master nodes. And for specific master nodes, you go down to leaf nodes. So this is what I can say related to the efficiency. But again, it starts with the quality and completeness of your metadata. If the metadata is complete and error-free, you should theoretically be able to achieve 100% efficiency. Okay, there's another question. Why the data, number one, is important and a relevant topic? Why to invest into the money and effort? Yes, I think that there are many use cases that we can cover with these data lineage analysis techniques. You can, for example, save a lot of money on specific testing. As I mentioned, the use case for nearest neighbors, you can identify which tables have changed their neighbors, and then you can focus your testing only on those objects. Of course, there are lots of regulatory requirements related to data lineage tracking. Nicely visualized data lineage gives you a good digital map for your enterprise architects who can better understand what happens with data in which systems across the whole organization. Or in many organizations, there are modernization projects that they use for decommissioning of legacy systems. And you can imagine that if you decide to decommission a legacy system, there are lots of dependencies, and you may not be brave enough to simply switch off that system. You usually want to analyze what happens, what are the impacts of closure of such system. And in that case, you run data lineage analysis. So you can save really a lot of money, or you can imagine that you do some errors in changes of your system. You implement new version of your system, and it causes several problems, several errors in your data architecture. It starts producing erroneous reports, for example. And you do this backward analysis, and you want to understand what happens, what is the root cause for your errors, where it is originated, and so on. So investing into data lineage analysis, and I admit that these are not cheap projects to implement data lineage and metadata management systems, but definitely the business case are there, and these projects and these solutions really are paid off. Okay. Maybe the last question from anybody? And if not, I would like to thank you very much for attending this webinar, and for your time and patience with us. And if you have any questions related to data lineage or metadata management or data landscape mapping, please do not hesitate to contact us, and we will talk about these topics more in detail. So thank you very much, and see you at some of future webinars that we are going to produce for sure.